contributor talks. And the first invited talk now will be by Yuki Minamoto from Fixstars Amplify Corporation about black box optimization with quantum annealing. Thank you very much.
Okay, thank you, Matthias. Hi, everyone. First of all, I'm Yuki from Fixstars Amplify Corporation. And first of all, thank you, everyone, for coming here today. And we would like to thank the organizers for having us here and giving us also. The reason why we chose this the topic is that, of course, this is something we are doing to keep our campus running happily, but also we think black box optimization is really a good application for quantum annealing. So please hear me out. Here is the list of contents. So today's talk, I want to give from the perspective of application rather than some technical aspects of quantum annealing itself. So if this is something you are not very interested in, apologies. So first, I'd like to do some introduction about our company and about our products, because yesterday, I kind of realized that 1/3 of the audience don't know who we are and what we are doing. And then after that, I'm going to start talking about black box optimization before summarizing today's talk. So who are we? So we are Fixstars Amplify Corporation, and we are operating quantum computing cloud platform for combinatorial optimization. So this platform is called Fixstars Amplify. It's the same name as our company, so it's a bit confusing. But Fixstars Amplify Corporation has been founded in 2021 in Tokyo, and our CEO is Mr. Takuchi Hiraoka, and our CTO is Dr. Yoshiki Matsuda. Both of them are sitting here today. I don't see people. Yeah, so if you want to talk to them, please talk to them. A little bit of fun fact about them. Mr. Hiraoka graduated from University of Tokyo, and his supervisor was Professor Furusawa, who is quite famous for optical quantum computing. And Dr. Matsuda, his PhD supervisor was actually Professor Nishimori. So these guys have a quite good pedigree in terms of quantum computing and quantum annealing. So what does Fixstars Amplify do? So again, as I said, Fixstars Amplify is our product, which is a platform for combinatorial optimization. So Fixstars Amplify consists of two environments, namely development environments and execution environments. So our development environment is called Fixstars Amplify PK, software development kit. This is essentially a Python library which allows fast and easy implementation of combinatorial optimization. And our execution environment is called Amplify Annealing Engine, which is a GPU-based idle machine that runs on cloud. So Amplify Annealing Engine has a capability of solving really big combinatorial optimization problem. To be specific, it can solve 131,000 bits for fully connected coupling problems and 262,000 bits for loosely connected coupling problems. So Amplify Annealing Engine can solve many of real-world problems already. That said, our platform, Fixstars Amplify or Amplify SDK, supports various solvers as well, other than Amplify Annealing Engine, including quantum computers, of course, with a QA algorithm, and quantum annealing machine, and other IP machines, including Fixstars Amplify Annealing Engine, but the ones operated by Toshiba and Nishi, which is the legacy, as well as other like software-based optimization solvers like Grow. Why do we do that? Despite that Amplify Annealing Engine alone can be capable of solving many, practical problems. Because one of the purpose we are doing this business is to facilitate social implementation of combinatorial optimization in both short and long terms. So I think it's fair to say that combinatorial optimization is not well recognized or utilized in real business world as a very convenient tool for like a decision making, for example. We think that people, like engineers, should start using combinatorial optimization for their business, like a decision making process. And at the moment, they should use these machines, other type of idle machines, because some of them are capable of solving fairly big problems, and they are relatively cheap to use. But of course, eventually, these quantum computers or quantum annealing machines are fully mature. And when that happens, of course, these machines will be nothing compared to other type of Ising machines. Quantum computers with QA algorithm or quantum annealing machines probably will be capable of solving really big problems really fast and probably with very high accuracy. And also, we can expect they will be very competitive cost-wise. When that happens, our users can switch from using these machines to newer and better machine perspective. But also, even within the same, within these machines, different machine has different capability, different technical features. So maybe users should be able to use, choose which machine they use, depending on the type of formulation, type of combinatorial optimization problems. But at the same time, we know that the changing one machine to another is a bit of a headache because different machine has different technical features or different API specifications. So essentially, if you want to change one machine to the other, you need to rewrite almost entire code. So basically, Amplify decay absorbs all the differences between different machines. And also, it can absorb the difference between user's formulation and machine that the user wants to use. So for example, if the user wants to use Amplify annealing engine, which is kind of cubical solver, but somehow user's formulation includes higher order polynomial or constraint or variable that is other than binary. In that case, Amplify's decay automatically convert variables from, for example, integer or real to the binary, and then penalize the constraint, and also reduce the order of polynomial in the user formulation, so that user can use Amplify annealing despite the type of their formulation. So how it is, what it is like to program using Amplify decay? Again, Amplify decay, it's fast and easy. So if your combinatorial optimization problem can be formulated like 1 minus Q0 and Q1. Here Q is a division variable, and which has constraint, one hot constraint, like something like this. You can formulate and implement your formulation, something like this. So your objective function equals 1 minus Q0 and Q1, and your constraint C equals 1 hot of Q. So exactly the same as the equation here. So it's quite intuitive. And that formulation, you can choose a solver that you want to use. You can choose Amplify annealing engine, but you can also use, for example, D-Wave or other Ising machines made by many other companies. And once you do that formulation, choosing a solver, you can just execute the optimization. And any necessary processing or converter process are done by Amplify CK in background. So all user need to do afterwards is just receive a solution and evaluate the solution. So it's very simple. Because Amplify SDK is quite easy to implement for even those who are kind of new in the field of combinatorial optimization of quantum annealing or surrogate annealing, it's quite easy. And also the Amplify annealing engine alone is very capable of solving fairly large problem. Fixstars Amplify platform is now used in many different fields, and some of them already operating in their daily business as well. These fields include some production planning, especially high mix and low volume production, because for which the planning is really, really difficult, and staff assignment in various industries, and energy management, because nowadays we have heterogeneous energy sources for which we want to come up with best energy mix almost real time. And for this kind of problem, combinatorial optimization with simulated annealing or quantum annealing is really useful. Adverse allocation application in major industry, and the research and development includes some material design, physics simulation, and black box optimization, which I will talk in the next slide. And other kind of relevant study, you can look up on Google Scholar. There are many studies carried out which are using the Fixstars Amplify platform. We also publish some demo example programs on our website. If you Google Amplify demo, you can see example programs, many of them. And most recent demo program is about, it's a font is very small, but it's about portfolio optimization, in which Fixstars Amplify is used to optimize the investment. Portfolio optimization example utilize actual market price information, price data as well. But there are other interesting toy models as well. So if you are interested, please Google. So Fixstars Amplify is expanding in various fields. Now we are supporting 10 solvers, and we plan to add more solvers because different solvers have different capabilities. So solver is good at one thing, and the other solver is good at the other things. Our users spanning over 700 corporates, institutes, and universities. And as of today, we've been in service for about 3 years. And Amplify annealing engine alone processed over 45 million requests. Actually, these numbers are big. This number is a bit old. I need to update, but at least they have like roughly 45 or 50 million requests processed. Okay, enough about Fixstars Amplify, and now I'm going to start talking about the black box optimization, video. So what's the difference between typical combinatorial optimization and video black box optimization? Probably most of you guys already know because you are smart. But just in case, let me overview. So in usual combinatorial optimization, first, of course, you have a optimization problem which need to be formulated. For example, for production planning, you have to formulate. You can formulate something like this. Basically, this is a quadratic formulation of decision variable Q. Or for traveling salesperson problem, you can formulate something like this. Again, this is quadratic expression of binary decision variable Q. Of course, as long as you're using the Fixstars Amplify, the formulation doesn't have to be quadratic. You can use third order, fourth order, with or without constraint. And you can also use like an integer variable or real variable as well. But anyway, you have to explicitly formulate your optimization problem. And once you do that, usually you have to do various conversions, logical, physical conversions. But as long as you're using Fixstars Amplify, you can just execute your program. And then the solver you choose to solve your optimization problem to which the formulation is really, really difficult or impossible. You know, the problem is impossible to formulate includes, for example, optimal alignment of spatial measurement sensors to minimize error of spatial measurements. I used to be a researcher in fluid mechanics, and I used to do this kind of measurement many times. And each time I have to find the optimal alignment of spatial measurement sensors. And we have to do it like a trial and error many times. Or finding the experimental condition or simulation condition that yields the result which is close to the target experimental result. So this is basically the inverse problem. But here, the error or the closeness, the black box functions, they are something you cannot explicitly formulate, right? So how people do to optimize this kind of problem is, of course, many trial and error based on their experience and some gut instinct, right? If you choose to use appropriate black box optimization method, you can expect to reduce the number of trials to reach a certain optimal level. So this is what the black box optimization is. But the difficulty is, again, these black box function is black box. You don't know the formulation, or you don't know the gradient or landscape of the function. So how do you optimize for that kind of problem? So typically, for video approach, for video problem, people use serial optimization method. So this famous Bayesian optimization is one of the serial optimization methods. And in this method, serial optimization, you basically repeat cycles for black box experiment or numerical simulation. And this X is your experimental condition or simulation condition. And you want to optimize the value of X in black box optimization plot. So the step number one, you first construct training data. So let's say you have 10 randomly generated input vectors. And for these input vectors, you perform your experiment or numerical simulation 10 times. We call it like an evaluation of your black box function. But anyway, you perform experiment numerical simulation 10 times. And now you get 10 samples of input output pairs. And this is something you can use as training data in the following process. And after that, based on this training data set, you construct a model function GX, which is supposed to mimic fx. And after that, you obtain x hat that minimizes gx, right? So this is where optimization happens. But this x hat is just minimize gx, but that does not necessarily minimize the original black box function fx. So you have to evaluate your black box function fx using this input vector x hat. And now you get another new input output pair. So you add that new input output pair to the existing training data. So now your training data is bigger. Then go back to step 2. Using that a newer, bigger training data set, you construct a model function GX again, obtain x hat again, and then evaluate the black box function again. And you repeat this cycle over and over again until you obtain solution that you satisfy. The idea of black box optimization, you want to minimize this number of cycles by choosing how you construct a model function and how you perform this kind of optimization, right? So the keys are how do you construct a model and how to optimize the model. These are 2 keys, and different black box optimization methods, including Bayesian optimization, have different approaches to these problems. So here is a summary of which method use what kind of approaches for these 2 key points. So famous Bayesian optimization, the model function, what they call original function, they use expected improvements, upper confidence bound, lower confidence bound, blah, 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 because many people working on Bayesian optimization. This is very traditional method. And for these models, they fit coefficient by analytically. And optimization acquisition function, you can of course use a grid search or random search, something like that. Maybe it used to be like that. But at least nowadays, they use quasi-Newtonian method like BFGS. That's the popular method. So there's a variant of Bayesian, many variants of Bayesian optimization, but probably most interesting one is this BOCX, the Bayesian optimization for combinatorial structure, which is originally proposed by Baptista and the project. In the BOCX, the fitting is done by given sampling. The reason so that they can use semi-different programming for optimization to reduce the cost. And this semi-different programming is later replaced by simulated annealing. So therefore, total annealing is also usable by hardwork and Amplify. But yeah, this is one variant, very interesting variant of Bayesian optimization. But anyway, the typical Bayesian optimization has one big issue, which is called cursor dimensionality. So this happens especially when your input dimension B. So input dimension is basically the number of addition variables you have to optimize. So when input dimension B becomes large. So what is large means typically people say around 20 or 30. But for sure, typically you cannot use Bayesian optimization when you have addition variable 100 or 200 or 1000. This is called cursor dimensionality. But we actually have many users who want to optimize for a number of addition variables. It's very difficult to tackle this problem based on optimization. A few years ago, there is a new like a video method was proposed by a group of group in Japan, which is called FMQA. So in FMQA, the model function is based on factorization machine, FM, which is a machine learning model described in the second order polynomial. Because the model is machine learning, the fitting is done by machine learning. But this machine learning is relatively cheap because this is just a second order polynomial, so number of coefficients or number of actually years with many different users for many different problems. We find not just Fixstars corporation, but also our users found some like a drawback, some possibility of improvements in FMQA. So we came up with like a kind of improved FMQA, which is now called kernel-QA. The relevant paper will be out very soon. But in this kernel-QA, which I describe later, the model is based on second order polynomial-based kernel. So basically, again, the same as FMQA, the model function is second order polynomial. The fitting can be done analytically, but because the model is second order, you can use again the quantum annealing or simulated annealing for optimization. Here is a little bit of detail of FMQA. So again, FMQA is proposed by a group in Japan in this paper in material informatics field. So the factorization machine FM can be expressed something like this. You see the constant term, linear term, and then quadratic term. There's one hyperparameter in this model expression, which is K. When K equals D, D is the input dimension. The GX, the model is used through interaction terms. So from modeling viewpoint, this is a better model. However, in a BBO context, because the idea is to minimize the number of function evaluation. So basically, you don't have many data sets. In which case, best to use a small k to avoid overfitting. And empirically, based on our experience, k equals 10 is actually sufficient regardless of d or fx complexity. So k is not really a hyperparameter in the context of BBO. And also, this is often our user misunderstood because FM is machine learning, but a model error or a loss function value is irrelevant when it comes to BBO. But what is important is cross-correlation coefficient between true and predicted value. So if even like when the model error is relatively large, as long as cross-correlation coefficient is positive and relatively close to 1 or well over like 0.5, then you likely achieve what you want to do with BBO. But even when model error is very low, which suggests that you're having a good model, but sometimes it happens in a machine learning that the cross correlation coefficient is negative. If that happens, it's likely that you don't get good optimization. So as I said, we've been using FMQA in the past 2 years with different users, different fields. Originally, FMQA was proposed in the material science field, and first 2-3 FMQA applications are in the same field. But when we saw this, we kind of knew that this can be used in the highly nonlinear problem in general, other than material science field. Using some toy models, some of them are published in our website code. So this line is just an introduction bits, but this line is for material optimization. So kind of similar, like how to say, application the original paper does. But the third example is in the field of chemical plant. So basically, in this example, we use FMQA to optimize the operation condition of chemical plant. Of course, we cannot really operate actual chemical plant in the demo program, but we developed a simulator of a chemical plant based on like partial differential equations. And based on that simulator, we optimize like operation condition of chemical plant to maximize the production rate. using FNQA. And in the fourth example is we use FNQA and the fluid simulator, which we also developed, implemented in the example code to optimize the shape of aerofoil. Of course, again, so this is here something I want to emphasize. So FNQA utilizes quantum annealing or simulated annealing basically Q1, but you can also use integer variable or real variable. This is one of the examples. Of course, you need to introduce some variable encoding, but you can use these variables as well. The last example here is a little bit more interesting than the other, in my view. So in this example, FNQA, so in the city, there are many traffic lights, right? So if you control these traffic lights optimally, then you can expect, the traffic congestion. In this example, it's possible with FNQA, right? So first we implemented the city traffic simulator using multi-agent simulation method. Okay, so there are cities, there are a bunch of traffic lights, and then we use FNQA to optimize the control of these traffic lights to minimize the city congestion. So all these examples are available. You can see all the codes and everything to see how FNQA can. But there are also some applications our use, but our user field includes it's quite range the range of field, including chemical, pharmaceutical, food, automotive, electrical communication, energy, and others. And the purpose of using FNQA is also diverse. Some use it for inverse problems and machine learning for cost reduction and accuracy improvement. This has something to do with the presentation on the first day. And component selection, design, development, material dependent optimization, and of course you can use FNQA for multi-objective optimization and simplification of physical models, and etc. And here is, of course, most of these examples. Some of you are very lucky, maybe. Right after this conference, there will be 2 domestic conferences, both are happening in Sendai. I know the 1/3 of the audience came all the way to Japan, and I believe after this conference, you guys have many very exciting plans ahead, maybe exploring Japan. Some of you go to Kyoto to enjoy historical city, some of you stay in Tokyo to enjoy some nightlife, maybe. I highly suggest you guys to go Sendai, which is north part of Japan. Sendai has very nice food, scenery called Matsushima. It's very historical and very beautiful scenery. You should go have a look. And on 25th, which is Japan Society for Mechanical Engineering, Mechanics Division meeting. Here, Kawasaki Heavy Industries is one of the real-world problems that our customers or users trying. This is really nice. This will be very nice presentation. And what is good about it is that conference is in Japanese, but I heard that their slides will be in English, so you can also understand to some extent. And there will be another conference 3 days later, JSA Congress. So this is Japan Society of Automotive Engineers here. And here, and Amplify, myself, will present a simultaneous design optimization of vehicle body structure for multiple vehicles using FNQA. This study is crazy. So what is crazy is this is basically multi-objective optimization. So there are multiple black box functions. But the thing is, there are a bunch of constraints as well. And these constraints themselves are also black box. So this is already difficult, but what's more, the number of decision variables, the real decision variable that they are considered is well over 200. So it's really big black box optimization problem. But they successfully optimize their problem using FNQA with their laptop and our IT machine. There are other groups or other like a big company actually trying the same problem using, for example, 6,000 parallel processing supercomputer. They couldn't, but Mazda did. So this is a really good study. I highly recommend if you have time, drop by Sendai and join this presentation. Okay, improving QA-based PBO. So as I presented, we've been using FMQA 2 years. FMQA is a very strong tool, have a big potential, especially for large dimension problems, as I explained briefly. But while we are using FMQA with our users, we not just Fixstars Amplify Corporation, but also our user noticed some drawbacks, some room of improvements in FMQA or QA-based PBO method. So one important drawback or possibility of improvement is that the FM used in FMQA. So FM training, this is basically machine learning, and compared to other type of machine learning, the FM training is relatively cheap, but still it's expensive. Sometimes can be a bottleneck for the computational cost. That's some of our user complaints. And also, FM training machine learning. So the training requires some tuning others sometimes. There are various parameters like epoch, batch size, learning rate, etc., etc. And there are quite a large degree of freedom which you can tune these parameters. And sometimes it's difficult because this is completely a machine learning field, and most of our users who are interested in combinatorial optimization or black box optimization are not necessarily experts in the machine learning field. So our skill user says, is there any easier and simpler surrogate model? Can you make it? And we made it, and we put the name kernel-QA. In kernel-QA, the surrogate model is expressed something like this. GX is expressed something like this, which is basically based on the second of the polynomial kernel function, as I explained in a few slides back. The idea is this, I don't deep dive into the mathematical detail in this presentation, but as I said earlier, our material will be out very soon. So if you register as Fixstars Amplify user, which is for free, you will be receiving email once our paper is out, and you can have a look at mathematical detail. But the idea is you can construct model analytically, which is very good for our user. So what you can expect from kernel-QA, first, as I said, fast model construction, right? Because our new surrogate model can be constructed analytically, whereas FM is need to be machine trained, which takes some time. Not a lot of time, but it takes still some time. So, and the surrogate model itself is better because in this analytical model construction, we use representative theorem, which yields globally optimal model coefficient, whereas most machine learning is performed by considering, for example, stochastic gradient descent, local minimum, local optimum, which is not good, especially in terms of PBO. And this is on par with FMQA because we can use quantum annealing or simulated annealing on par with FMQA. The optimization is very, very fast, even for large dimension problem. Whereas Bayesian optimization, this optimization phase takes a little bit of effort, especially for the large dimension problems. So this is something you can expect from using kernel-QA, using different types of test functions, and also some of users' real-world problems using kernel-QA. And this is just one example. Here we use Rust origin function as a test function. Yeah? So two-dimensional Rust origin function would something like this. So basically, this function has many local minima, and you don't want to track these local minima too long, yeah, so that the optimization progresses very nicely. We considered real variables, and not just a two-dimension. We considered dimension of 5, 10, 20, 40. So in case we have to consider every fairly big size black box optimization. We performed this optimization with kernel-QA for each case 10 times, or in the Bayesian optimization each time 10 times. We analyze statistically, and you see what you see is average and variation. And then we can see, especially for the larger dimensional problem, Bayesian optimization shows some effect from causal dimensionality. The optimization doesn't progress almost at all, but kernel-QA, the optimization progresses like almost monotonic manner. We also do the same test for concerning binary variables as well, from 40, 80 until 640. So it's really, really big problem. But the result optimization shows very strong effect from the causal dimensionality, whereas kernel-QA does not. In terms of computational performance, so this shows the evolution of elapsed time from the beginning of the optimization. It's almost linear, which means the elapsed time per cycle is almost constant, which is quite unique compared to Bayesian optimization of FMQA. But that's it. QA-based DDO, like FMQA, are complex to implement, even with the aid of Amplify's decay. We have to know about machine learning, quantum annealing, and blah, blah, blah. So we developed another Python library for Amplify DDO to make QA-based optimization very, very easy. So I don't go detail, but Amplify DDO leverages Fixstars Amplify's features. Like you can use various variable types and VS solver as well. You can consider software and hardware constraints very, very easy as well. So this is what it's like to using Amplify DDO. So if you implement one of our demo code, which is publicly available by using Amplify scales, right? So if you don't use Amplify scale, you have to write probably thousands of code. But if you use Amplify SDK, even if you use Amplify SDK, you have to write, like, for example, 250 lines of code to perform FMQA of one of our toy models. If you implement same optimization problem using Amplify DDO, you can just implement 30 lines of code and to do the same things. So it is very handy. If you are interested, please contact us. We are releasing in the beta version now. So here is summary. As I explained, DDO seems really a good application for quantum annealing because use of like a second order polynomial and QA in an optimization step is really, really important, especially for the large dimensional problems. And now manufacturing computer-aided engineering, right? And because of the very high performance of like their computer, nowadays you can perform really big simulations, which comes with many, many parameters that the engineer want to optimize. So the black box optimization with large dimension problem is not avoidable. We have many, many customers who tried like a conventional black box optimization method, like a Bayesian or genetic algorithm, and they are not very successful and can similar situation. So in that case, the QA-based DDO has a really strong potential. And if you want to see the QA-based DDO, namely FMQA, for real-world problems, again, you should go to these two conferences in Sendai in similar times. Not just conference, you can enjoy the history, scenery, food. Sendai also has a Fox village. You can pay Fox. So I think you can enjoy as well if you go to Sendai. That's something I highly recommend. And I myself will be at this conference entire duration, right? So if you find me, it's nice if you say hi. So here's a summary, and thank you for your attention.
Thank you very much. I see already there are questions over there.
Thank you for a very interesting talk. Can you specify when Mazda used 200, they had 200 elements for you said for this optimization. How big of an IC machine did they need?
Well, in Mazda case, their black box function is for actual like cards, free cards that they are producing. But instead of using physical simulations, they use some model function for the purpose of benchmark, right? So the computation costs to evaluate black box functions are almost zero in this case. So the computation time they needed is purely for optimization purpose. And for this Mazda case, they used our IC machine, Fixstars annealing engine, Fixstars Amplify annealing engine. And the overall computation time is about 30 hours by using like 1,000 optimization cycles.
Okay.
Yeah.
And how they used the full machine of 100,000 spins? So how much do they need?
So because this is roughly speaking, they have a 220 something like real variables, and each variable can be discretized by using, for example, let's say 10 binary variables. If that's the case, then maybe they need like 2,000 bits plus some like hard constraints, the auxiliary what is like some supplemental variable required for the constraint condition as well. So 3,000 at most.
Yeah, impressive work. Looking forward to trying out your service myself. So, so there's a training aspect and the actual optimization aspect. For the training, I imagine you need a GPU or a CPU for that. You can't use say a D-Wave machine or a digital annealer for the training. So then how much of the computation is done by the annealer versus, CPU, GPU, and other resources?
So I think this is the beauty of black box optimization. So in kernel-QA, yes, this model construction requires machine learning, but that doesn't require high-step GPU. Actually, the reason why is the size of data set is really small. In the Mazda case, they have to deal at the end of the cycle. They have to deal with training data, which contains only 1,000 samples. So the computation, the machine learning, doesn't cost too much in terms of memory or CPU hours compared to other typical machine learning, right? And in terms of computation, I don't know the exact time required for this model construction as that case. But if I remember correctly, the annealing, I think the annealing timeout is something like 5 to 10 seconds each time. So I said like if they performed like 1,000 cycles, which requires 30 hours, out of which let's say 10 seconds for annealing times 1,000 required for annealing overall. I think the rest is the time it took for machine learning. Yeah, so it's fairly less computationally expensive compared to like nowadays LLM or other kind of machine learning model requires really massive training time. Compared to that, it's still small.
Thank you.
All right, and then the next speaker maybe already sets up. And in the meantime, maybe very brief explanation. You mentioned that a problem where even the constraints for black box.
So
you mentioned in the constraints for black box.
Do it for the choosing like a thickness of their upset, the metal plates. You know, when you manufacture a car, you need a lot of metal plates, and the thickness of plates are different depending on which part you're manufacturing. They want to like maximize the number of metals which have the same thickness, but they also have to consider like a crash test or like a rigidity and stuff like that. These crash test result in the rigidity, that kind of thing is conflict.
Okay.
That they have to.
Thank you very much. Then let's give it up for Yuki again for a nice talk.